Okay, in terms of stuff, deadlines remain unchanged, so exam 3, exam 4, quiz and assignments part 4, deadline on this Friday, but a couple Fridays from now, April 26th, 11 to 9:59 p.m. Exam 5, the exciting final, deadlines of Wednesday of finals week at 5 p.m. As I noted before, the best 4 exams count. They're 40%, best 10 quizzes count, 30%, best 10 assignments, also 30%. And Blackboard doesn't delete or hide the things that are being dropped. You can still see them, but it's doing the calculation by using the best 10 quizzes, best 10 assignments, best 4 exams. Also noted before, anything that hasn't been done is already is a 0, so that way there's no shocking surprises of like sudden zeroing of things at the end. And so to see if you need exam 5, you look at your overall grade, that's where you are for real in terms of your grade. If you do more stuff, if it's not better than what you've already done, your grade stays the same. If it is better, then it improves. And to see if the final could make a difference, the thing to do is get the grade estimator, put in your best 3 exams, quiz overall grade, assignment overall grade, hypothetical 100% for the final, and see if that's a letter grade or more better than your true overall or current overall grade. If so, people are taking it. If not, you change nothing. Before going on to our new stuff in Chapter 8, Categorical Logic, anything about any other stuff to be or there's been that needs more stuff? Okay, so last time we began our adventures in categorical logic. And the idea is it's the logic of classes, about things being in a class or being out of a class. And we saw the notion of a categorical claim, and we saw the 4 categorical claims, the A-E-I-O claims. And then we looked at one of the rules, the conversion rule. And as we saw, there are 3 of these rules, and they do a particular thing. Conversion does it by switching the subject and predicate, and it works in the case of E claims and I claims because they're symmetrical. So when you flip them around, they still mean the same thing. And in terms of what it means for the rules to work, it means if you apply them, the sentence you get informally means the same thing. More formally, it retains the same truth conditions. Now we turn to rules 2 and 3. Our version, in some ways, more complicated, but in other ways, somewhat simpler. Now, in terms of what it does or how to do it, here's how you do it. The first step is you replace the claim with the claim directly across from it on the square of opposition. Now, in normal claims, less involving the square, what happens is that all becomes no, some becomes some or not, and vice versa. So in a way, you change the, metaphorically speaking, change the polarity of the claim. And I'll symbolize this by a little plus minus rotate. So all becomes no, no becomes all, some becomes some or not becomes some. The second thing that happens is that the predicate term is changed to its complement. Now in this case, the complement is not, compliment with an I saying something nice about it, like, why predicate? You're such a great predicate. It's this. The complement of a term is all the things that that term doesn't refer to, everything outside the term. In terms of like classes and sets, the idea would be if you get a set or a class, the complement of that set or class is all the things that are not in it, all the stuff outside. So to use a bit of metaphor, the complement of this room is all of the things outside of the room. Now, the easiest way to do this is take the predicate and simply negate it. So, again, the example of the room, the complement of the room is all the stuff outside of the room, so it would be all the things that are not in the room. So, things not in the room. Now, in most cases, and that's an example of one where it doesn't work so well, you can typically just take the predicate term and change it into non. So just tag non onto it. So P becomes non-P. Or if you already have non-P, it goes back to being P. Now, as that example shows, sometimes it works fine. So if you're talking about cats, the comma would be non-cats. But if you take something like, you know, things outside this room, or things inside this room, the comma of this room would be things outside. If you put non-things, that would be weird, because it'd be things that aren't things, which would be possible. But we'd say things outside the room would be the comma. But most of the time you can just tag on non, except like examples like that where it'd be weird to say, you know, non-things, you know, non-things in the room. So that's how we apply it. So where does it apply correctly, and when do you use it? Well, in terms of when it applies correctly, this is what makes it simple. It applies correctly to all four. So there's a question on an assignment, quiz, or test, and the question is blah, blah, blah equivalent to its obverse? The answer is always yes. You don't even have to look at what it is, because every obverse is equivalent to its original, just the way the rule works. Because in a way, the logic behind this is double negation, because you're negating the claim, and then you're negating the predicate. And of course, in logic, not just says the original thing. Excuse me. So if you say it's not non-raining, then you're saying it's raining, in kind of a roundabout way. So going through the examples, all S are P gets averted to no S are non-P. So if all cats are mammals, that would be no mammals are non-cats, which would be true. Because if you have any, you know, any mammal, well, we take any, if all cats are mammals, that means that no cats are non-mammals. So take any cat, it's not going to be a non-mammal. With the E claim, no S or P, that becomes all S are non-P, which, you know, makes perfect sense. If no Republicans are Marxist, that's the same thing as saying all Republicans are non-Marxist. And then some SRP, this becomes some SR not non-P. So if some Democrats are socialist, the aversion would be some Democrats are not non-socialist. And of course, not non just says the original thing. And then for the O claim, some S are not P becomes some S are non-P, which essentially says the same thing. Now, when is this used? Well, it's used, as you might imagine, when you've got one of these, because these, on this side, are not in standard form. So the claim no cats are non-mammals, not standard form. The claim all Republicans are non-Marxists, not standard form. Because standard form is, it's got to be one of these four. And so if we see this, or this, not standard form, and aversion allows us to get into standard form. Now typically that would be the way you would go, because if you're trying to get into standard form, you'd always start with one of these and get it back to that. So to tell which rule to use, you look at what you're starting with. And so you would use conversion, as we saw, when your subject and predicate are in the wrong place, and you have to flip them around. You use aversion when you've got this double negative scenario. So how will this show up on quizzes, assignments, etc.? Well, just like with a conversion, it could be a true-false question about the definition. Also, there'll be an assignment where it will say, what is the aversion of, you know, all cats are mammals, and then you pick, you know, from the options. And of course, it would be no cats are non-mammals. And then also, as I mentioned before, there'd be a question about whether it's equivalent or not. So if it says, is this equivalent to its aversion, the answer is always yes, because aversion works correctly for all categorical claims. Okay, so the important things to know about aversion are, how does it work? I like this. In a practical matter, you reverse the polarity, no becomes all becomes no, some becomes some or not becomes some. And then you take the predicate term, replace it with its complement, and again, 99% of the cases, you can just tag on a non in front of it, and it works. But in some cases, you need to be a little, more complicated. So you're talking about people who took the exam, you wouldn't say non-people who took the exam, you would say people who didn't take the exam. It applies correctly to all the sentence types, and it's used when you've got this stuff, and you got to get to the standard form. Before heading to our third and final rule, anything about a version that needs more ob or vert? Third and final rule, contraposition. This one is also more complicated, involves doing a few, two steps, and like conversion, it only applies to two of the sentence types. So instead of being able to just say, yeah, it applies to everything, only applies to two. Unfortunately, it's the two that conversion doesn't apply correctly to. So here's how contraposition works. Step one, you switch the subject and predicate. So, like conversion, they swap places. The next step is that we replace both the subject and predicate with their complements. And again, like I mentioned before, the easiest and fastest way to do this is simply stick non in front of them. So S becomes non-S, and P becomes non-P. And those are the steps. Now, as I mentioned, in terms of where does it apply correctly, it applies correctly to only two, namely the A claim and the O claim. The E and I claim doesn't apply correctly to. So conversion will apply to these two because they're symmetrical, and contraposition, because of this second step, the negation part, it makes it apply to the A and O claims. So when did you use it? Well, you use it when you get this scenario, namely, like conversion, your subject and predicate are in the wrong place. And the way you know when to use contraposition as opposed to conversion is instead of them just being in the wrong place, in the wrong location, they're also negated. So if they're in the wrong place and both negated, it's a job for contraposition. So for example, with all S or P, that contraposes, its contrapositive is all non-P or non-S. So for example, all cats are mammals contraposes to all non-mammals or non-cats, which makes sense. If you have a bunch of non-mammals, none of them are going to be cats. With the E claim, no S or P, that contraposes to no non-P or non-S. But this doesn't work properly because no S or P could be true, but no non-P or non-S could be false. As an example, if we have no Republicans or Marxists, we would get no non-Republicans are non-Marxist, which clearly isn't true, because this could be true, no Republicans are Marxist, but there could be many non-Republicans who aren't Marxists. I claim some S or P contraposes to some non-P or non-S, some non-P or non-S, and it ends up being not correct. And the reason why, again, is this could be true and this could be false, or this could be false and this could be true. Lastly, with the O claim, some S or non-P contraposes to some non-P or non-S, and this does apply correctly because it says the same thing. So if some Democrats are not socialist, it would be some non-socialists are not non-Democrats. And so the recap for this is, how does the rule work? Well, subject and predicate switch. Then you reverse the polarity of both the subject and predicate, and there you go. It applies correctly to A and O claims, and it's used when you've got this stuff and you need this stuff. And again, the whole point of these rules is to go from non-standard form to standard form. Okay, so those are our three rules: conversion, obversion, contraposition. And their function is going from non-standard to standard. Now, as we'll see in the future, we get to truth functional logic. Contraposition also applies to conditionals, like if P, then Q. And that would become if not Q, then not P. We'll see more of that in the future. In terms where you might also see contraposition, standardized tests, for example, if the LSAT has a game section, and it's games in the same way kind of the Hunger Games is games, namely technically a game, but not one that's fun to play. And they use contraposition as a critical tool because people are terrible at negations, and also the one that involves conditionals, people are terrible at conditionals, so when they set up the games, they often put it in terms of negations and conditionals. And contraposition allows you to take negation at least and get it to something positive. So it can be useful there.
Like logic games, like that section.
Yeah, so they'll have something, like one of the typical games would be something like, if you don't have you get a game of like hats and scarves, you gotta put it on display. There'll be, say, 5 displays in the window, 5 mannequins, and then it'll have rules, like it'll say, if you don't have a blue hat, then you cannot have a red scarf. And then you have to figure out, like, what is that, what is that setting up? And it's saying if you don't have the red scarf, then if you have a red scarf, then you have a blue hat. And so the idea would be going through those rules and sorting out, what the questions, what the correct answer is. So it might say, for example, once you get all the rules laid out, it may say you must always have a purple hat on mannequin 2, and you must always have a green scarf on mannequin 5. Suppose you have a purple hat on mannequin 5, what must the scarf be on mannequin 2, 3, or whichever one. And you have to go through the rules and figure out where the scarf goes. And they're not really about scarves or apartment buildings, etc. They're just logic puzzles involving typically conditionals. They present the rules in true functional logic, and they'll give you a condition. You have to sort out with a diagram how to answer it. And they are technically games in a terribly unfun way. Okay, before moving on, anything about any stuff that needs stuff? Now, as mentioned before, sort of the end game of Chapter 8 is to get to testing syllogisms for validity. Now, the argument type for categorical claims, fortunately, it's pretty limited. There's one type. And so categorical logic, one kind of good thing about it is it has all kinds of limits, so it's easier to handle. So there's only 4 sentence types. There's only subject and predicate. And we only have one type of argument, namely the categorical syllogism. Now, we know from the past that a syllogism is an argument with 2 premises and 1 conclusion. So every categorical syllogism will have premise 1, premise 2, conclusion. And of course, what makes a syllogism is not that it has 1 conclusion, because that's true of all arguments. What makes it what it is that it's only got 2 premises. And that's all it means. To be a syllogism is 2 premises, 1 conclusion. So a categorical syllogism, what makes it categorical is the premises and the conclusion are all categorical claims. For example, premise 1, all Americans are consumers. Premise 2, some consumers are not Democrats. Conclusion, therefore some Americans are not Democrats. Now, as I mentioned, our objective is to go from normal English or semi-normal English to standard form, and then test the argument, the categorical syllogism, in standard form to see if it's valid or invalid. So how do we do this? Well, before we can test it, we've got to get the labeling of the terms, which then becomes kind of, in a way, somewhat confusing because we've already looked at, the S and P term for, look at in terms of the claims, also the various rules, but now we add in another term, the middle term. What makes it in some ways kind of confusing is we still have a subject and predicate term, but now we have an S referring to the minor term, the P referring to the major term, and the M referring to the middle term. And of course, these can serve as subject or predicate. So how does this work? Well, here's our three terms and what it means. The major term, symbolized by P, and the reason why it's labeled as P, is the term that occurs in the predicate of the conclusion. So if an argument is assembled properly, then what you do is you would look at the conclusion, and to tell what is your major term, assuming it's set up properly, that will be always the predicate of your conclusion. The minor term, S, is a term that occurs as a subject of the conclusion, so it would be here. And then M is a term that's not in the conclusion, but in both premises. So the way you spot the parts is, assuming the argument's in proper form, you gaze upon the conclusion, and again, assuming the syllogism is put together properly, premises in the right places, conclusion in the right place, and in standard form, the subject of your conclusion is your S term, the predicate of your conclusion is the P term, and the term that doesn't occur in the conclusion is your M term. As to why they call it major, minor, and middle, tradition, essentially. It goes back, I believe, to the Middle Ages, and they refer to them as the minor, major, and middle, and it just kind of stuck, and it's used to essentially label what they are. So why do we need to know what the SP and M terms are? Well, the answer is in order to do the test for validity, we got to know which one is which. Okay, so the recap, important things here are these. First, the only type of argument in this type of categorical logic is the categorical syllogism. And being a syllogism, it's got two premises, one conclusion, and being categorical, all of the parts are categorical claims. Assuming it's set up in proper form, and you've got it in standard form, all the categorical claims, the major term, the P term is always the predicate of your conclusion, the minor term is the subject of your conclusion, and the middle term, M, is always the one that's not in your conclusion. And as you can see, it serves supposedly to connect the two. So kind of the pattern of reasoning, what's going properly is you link S to M, you link M to P, and then you link S to P through M. So how do we do the actual testing and such? Well, here's how we do it. Now we'll look at two methods for doing this. First is the Venn diagram method. Second is the rules method. And they both work, they've both been tested. And also, as mentioned, if you take like a class of mathematics, they tend to use a different method, the Euler diagrams, but they still work. And there's probably other ways of testing it as well. But for whatever reason, philosophies embrace the Venn diagram. So the standard Venn diagram looks like this. It's our old friends, the two circles, the S circle and P circle, but with an addition. We now have a third circle, the M circle upon there. And of course, the S term is a subject of the conclusion, The P term is the predicate of the conclusion, and the M term is the middle term, the one that doesn't occur in the conclusion. Now, in testing for validity, there are essentially, once you get the diagram, once you get the argument in standard form with the diagram there, there's two steps where you're doing stuff, and a third step where you're just looking. So step one, you diagram premise one. Step two, diagram premise two. And then you don't do anything with a conclusion, except you gaze upon the completed diagram, and if you see the conclusion already there, then it's valid. Assuming you've done all the stuff correctly. If you look upon it and you don't see the conclusion already there, and it's been done correctly, you know it's invalid. So, mark premise one, mark premise two, look upon it, and it's all been done correctly, you'll see, literally see, whether it's valid or invalid. So how do we do those steps? Well, first example. Premise one, no Republicans are collectivists. Premise two, all socialists are collectivists. Conclusion, therefore no socialists are Republicans. So step one would be, of course, getting the argument, putting it in standard form, etc., what is already done here. Then once we have the argument in standard form, to know what is what, we look upon it, and so we know that socialist is our S term, because subject of the conclusion. We know Republicans is our P term, because predicate of the conclusion. And we know that collectivist, since it doesn't occur in the conclusion, is our M term. So we use this to do our diagram. So the normal blank diagram, of course, looks like this. Got just three circles, nothing going on. Next step is we diagram premise one, although you can diagram premise two. So if you diagram premise two first, that's fine, because it actually doesn't matter which order you do the diagramming in, although as we'll see a bit in the future, it can be somewhat more convenient to sometimes diagram out of order. So how do we know how to do the circle thing? Well, as mentioned before, one thing that's slightly confusing is we got the S and P terms, and then we threw the M in there. So when we go back to our two circle scenarios, we would go back to just using S and P. So the M term, can function as, will function as a subject and predicate. And so when we're looking at terms of the two circles, we kind of go back to talking about subject and predicate. And as I mentioned before, with our original ones, again, we just have the two circles. So you have all S or P, no S or P, some S are not P, some S are P. And so we use these two circles, collections, to do our three circle. So how do we do that? Well, as I mentioned back in those ancient days, when you've got a no or all, the third circle doesn't matter, because you're doing full-on shading, and so you don't stop at the border, you just keep on going over that border wall. So how would we diagram premise one? Well, here we have no Republicans are collectivists, so no P or M. Now, going back just to our two-circle approach, the subject of this is Republicans, and our predicate is collectivists, even though, of course, our Republicans is our P term, and collectivists is our M, our middle term. So diagram like this. We've got this being the P term, Republicans, and collectivists being the M. So we'd shade all the stuff in the P circle that's not M. Now, if we just shaded here and stopped at, stopped here, we would be saying all P or M except those which may be S, which is not what we're saying. So when you're shading, you ignore the third circle because you're talking about all or no. So always shade either cookie with a bite out of it, or crescent, or football. Any other shape would be wrong. So this is what it would look like. So we got no Republicans or collectivists. So we would say that none of these are these. So when we say no Republicans or collectivists, we're blotting this out. If we were saying all Republicans are collectivists, we would be shading here. Whatever we shade, it's going to be for all, always a crescent shape, and for no, always the football shape. So diagram premise 1. The next step is diagramming premise 2. And so in this case, we got all socialists are collectivists. So the socialist term is the S term, collectivist is the M middle term. So we'd be saying all socialists are M, so all S are M. So it would look like this. And then, since the steps are diagram premise 1, diagram premise 2, and then look upon it, we're at the looking upon stage. Now again, we don't mark the conclusion, so once you do premise 1, premise 2, you say, pens down, and then you look upon it. So how do you tell if it's valid or invalid? Well, what you're looking for is to see if the diagram, unmodified, gives you the conclusion with certainty. Because as you recall, a valid argument is such that if all the premises were true, the conclusion must be true. Not could be true, but must be true. So you have to be able to look at the diagram and say, 100% certain, if all the premises are true, then the conclusion must be true. So what we need to see is no socialists are Republicans, so we need to see no SRP. So looking upon this, we would need to see this area filled in, and we do. Now you might wonder, well, what about this other stuff? Does that affect the conclusion? And the answer is no, because what we need to see is the conclusion definitely true? And the answer is, yeah, we do have this, this other stuff, but that doesn't matter because what we need is this filled in. If we got that, the argument in this case is valid. And we get it, so it's valid. So in a way what we're doing is, if you were to mark the diagram with a conclusion, you wouldn't change it. So in this case, if we wouldn't shade it here, diagram with a conclusion, which we don't do, nothing would change. It would be this area marked off. So those are the steps. Give the argument to standard form, with everything in the right place. Then diagram premise 1, diagram premise 2, and then look upon it and see if the conclusion is definitely there. If it is, valid. If not, invalid. Before heading to the next example, anything about this that needs more stuff? Now what about some claims? Because as I mentioned back at the beginning, when we're doing some claims, some are, some are not, we're placing an X, and I mentioned that when we go to the 3-circle thing, the third circle matters. So we just can't just put it wherever, we gotta put it someplace definite. So the shading in some ways is better than putting in the X's, because with the shading, you don't have to worry about the third circle. You just do this or do that, no worries about the third circle. But when placing the X, third circle matters. So let's see an example involving the sum. So we have some S are not M, all P are M, some S are not P. Already in standard form, so we know what all the terms are, and we just got to do the diagram. So again, blank circles always look the same. Then we have some S are not M. So what we have to do is place an X that is S, but not M. Now, that means it's got to be outside of the M circle, so it can't be here or here, but it's got to be in the S circle, so it could go here or here. Now, we can't definitely place it here, because that would say some S are not M, and also not P. But we haven't got that. We just have some S are not M. If we put it here, we'd be committing to some S are not M, but are also P. But we don't know that. So what do? Well, what happens is what's called the floating X. So we mark it like this. It could be here, could be here. We can't say for sure. And we can't just like guess, because that just is not what's done. Now, the book places the X on the line. So they would do it this way. And that is, not wrong. But the reason why I use this is for a couple reasons. One is, if you're trying to place the X on the, directly on the line, it's kind of easy to get it kind of close. And so as a practical matter, you may miss the line, and it may be hard to tell, is it on the line or is it not? Kind of like in tennis or basketball, or baseball, is it in or out? Secondly, as we'll see, sometimes you diagram the next premise, you might have to shade over it. If you like put it on the line and then start shading, then you gotta like take that off the line and move it over, more work. And thirdly, and most importantly, when I was a freshman, that's what I learned. And so it just seems right because it's what I learned. But at least there are two other good reasons for it. But either way works. That's just one of these. So what do you do if something happens to, the X? Well, so we go next to our second premise, all P or M. And there'll be some cases where the second premise will affect the first one in terms of placement. So all P or M, this involves shading. And again, when we shade, we ignore the third circle. So we want to show that all P or M, so shade, shade, shade. Then we hit the border of the S circle. And if we stop there, we'll be saying all P or M, but also some are S too, but we haven't got that. We've got all P or M. So we shade on through. So what happens to the X? Well, when you shade, what you do is you, metaphorically speaking, push the X out of there or make it so it can't be there. So it's like closed off. So to use a metaphor, it's like saying, well, it's here or there, but, well, this area is closed off entirely, so it's got to be there. So what we do is, when you diagram premise 2, this is what happens. So this gets closed off, the X defloats, it lands here. So now we know definitely where the X is. So once we diagram premise 1, premise 2, the next step is to gaze upon it and see if it's valid or invalid. And the way we tell is this. We look at it and we see, does it give us the conclusion? Would we have to do anything to change it to give us the conclusion? So what we need to do is we need to see, to make it valid, we'd have to see there being an S that's not P. So we need an X here. And we look upon it and we see we've got that. So some S are not P, there we go. So the argument is proven valid. So when you get the X, floating, or potentially floating, again, one approach is to do it this way. The authors of the book also suggest, which is a good idea, is if you have a sum for your first premise, diagram premise 2 first, because the order of diagramming doesn't matter. It's not going to change stuff. So if you did premise 2 first, you do this, and then when you do premise 1, you don't have to float anything. You just put the X there. So it's pretty good practical advice. If you have a sum for the premise 1, diagram premise 2, save yourself the trouble of floating stuff in some cases. before pressing on, anything about that, about dealing with the X that needs any more stuff? So third example, premise 1, all P or M, premise 2, some S or M, conclusion, some S or P. So you got another case where we got some in there. And as always, the question is it valid or not? So, testing with a Venn diagram, first we get our circle of blankness, then we diagram premise 1. So that would be all P or M. So again, we shade the whole thing, and we ignore the third circle when shading because, again, when you're doing all or no, it means all or no. It doesn't mean all but, it means all. So it would look like this. So all P R M. Next, some S R M, so to place the X. Now in this case, when we're placing that some S or M, we gotta place an X somewhere in the S circle. It's also in the M circle. So it could go here or here. And again, if we don't know for sure where it goes, we don't get to guess or pick. We have to do that floating X, because saying some S or M means it could be in here somewhere, but we don't know. And if we definitely place it, then we're wrong. We'd be saying that if we put it here, we'd say some S or M and not P, which we don't know. If we put it here, we'd say some S or M and P, which we don't know. So could be here, could be here. So we end up with the X floating, and nothing tells us where it's definitely going. This would be a case where the X stays floating. Now, when you see the X floating there, you can be pretty confident that it's not going to be valid. Why? Well, none of our standard claims has, S, some S, R, M, or maybe P. We haven't had that as a standard form. So we know that if you see this and you've done it correctly, pretty sure that it's going to be invalid. But just to confirm it, the conclusion is some S, R, P. Now looking at it, this could be true. Maybe it is here, but we don't know. Could be here, could be here. So all the premises could be true. This could be true, this could be true, but the conclusion could still be false because the X could be here. Now, of course, it could be here, but with validity, we need certainty. It's going to be such that if all the premises were true, the conclusion must be true. But we don't have that. So this would be invalid. And that's how you test it and how you tell. Now, there are actually, as I recall from when I was a freshman, there are 72 valid syllogisms. And no reason to memorize them because you can test them, but there are 72 combinations that are valid. Now, any argument you get that's a categorical syllogism, you can apply the test, and again, every categorical syllogism is going to be valid or invalid. Before pressing on, anything about the basic test that needs any more stuff. And it works the same way every time. You take the English stuff, put it into categorical syllogism, standard form, get the blank diagram premise 1, diagram premise 2, look upon it, and you see the conclusion already there with certainty, valid. If you don't, invalid. Now, being arguments, they can of course have missing pieces. Now, one thing that makes categorical syllogisms easy to work with in this case is, if you know you've got a categorical syllogism, you would know exactly how many pieces are missing, because there's 3 pieces, and so if you haven't got them all, you know the exact number missing. So for example, If someone says you shouldn't give chicken bones to dogs, they can choke on them, it's only got 2 sentences, but it's got a pretty clear missing premise. So to build it into a syllogism, we would get premise 1, all chicken bones are things dogs would choke on. The missing premise, no things dog could choke on are things you give dogs. Conclusion, no chicken bones are things you should give dogs. And done. So categorical syllogisms are easy to work with because, again, they're so limited. You've got only 4 possible sentence types. You've got 3 terms, SP and M, and that's pretty much it. There's just not a whole lot of complexity to it. Now, as the authors say, like what the useful tool for any logic is replacing long phrases with letters, but kind of weirdly they used like C, D, and S for chicken bones, dogs, and should, but it would be even simpler just to use SP and M. So those are the minor complications. Now suppose you don't like diagrams. Is there another way to test it? And the answer is, of course, we've got you covered. To use an analogy, this is kind of like the command line version of testing, as opposed to the icon-based. Now, interestingly enough, you can test a categorical syllogism without using any Venn diagrams or Euler diagrams. You can just do it by 3 rules and looking at what you got. Now, in order to use the rules, we have to first go through one new concept. And this concept is distribution. Not distribution in the sense of like distributing wealth, like some of the Democrats purport to do, but distribution means this. In a claim, a term is distributed when you say something, the claim says something about every member of the class that term refers to. So if you have like all cats are mammals, if you're saying something about all cats, it's distributed. If you're saying something about all mammals, it's distributed. And if you're not, it's not. Now there's kind of 2 main ways to know when something's distributed and when it's not. One way is just memorize this handy table, because it shows what's distributed and what's not. Another way is just, you can kind of think through the claim, and it will tell you what it's talking about, all of the stuff. So first, the A claim, all S are P. Pretty clearly, the S claim is distributed because you are saying of all the S's they are P. Now, the P term is not distributed because although you're saying, for example, all cats are mammals, you're not saying something about all mammals, just all cats. Or you can just memorize that A claim, subject is distributed. In the E claim, everything is. When you say no S or P, it may sound odd, well, how am I saying something about all of them? Because it's an O claim. Well, here's how. You're saying of all the S's, they're not P's, and you're saying of all the P's, they're not S's. So if you say no Republicans are Marxist, you're talking about all Republicans, namely, they're not Marxist, and you're talking about all Marxists, namely, they're not Republicans. In the I claim, as you might imagine, nothing is distributed because it's some S or P. So if you say some Democrats are socialist, you're talking about some Democrats and some socialists, but not all of them. So nothing is distributed. In the O claim, well, this may seem kind of weird. You may think, is that a typo? And the answer is no. In a O claim, some S are not P. Seemingly oddly enough, the P P term is distributed. Why? Well, it's kind of an odd way, but still correct. Namely, if you say some Democrats are not socialist, you're talking about all the P's. Namely, that all the P's are not that. So, for example, if you say like a particular Democrat, like Joe Democrat, is not or Joe Biden is not a socialist, you're saying of all socialists, they're not Joe Biden. So it's kind of a backwards way of doing it, but technically correct. So I don't claim this is the most confusing. The predicate term is distributed. So why do we need to know distribution? Well, for the rules method. What's the rules method? Oh, good that you asked. It is this, the rules. So we have 3 rules. Rule 1, and this is a pretty useful one because it's pretty simple, you don't have to really work at it. The number of negative claims in the premises must be the same as the number of negative claims in the conclusion. Now, since there's only one conclusion, that means that if you've got a negative premise and you've got a non-negative conclusion, it's got to be invalid. If you have 2 negative premises, it's got to be invalid. If you have 2 negative premises and negative conclusion, it's invalid. 2 negative premises, positive conclusion, it's invalid. If you have a positive conclusion, negative premise, invalid. And this one is pretty useful because even though it's not going to catch all the cases, this will quickly catch quite a few. Rule number 2. At least one premise must distribute the middle term. In fact, there's a fallacy called the fallacy of the undistributed middle. And that's where the distribution comes in. So the middle term is going to be at least one premise that has the middle term and a distribution point. Lastly, rule 3. Any term that's distributed in the conclusion must be distributed in the premise. Now, if a syllogism makes it through all 3, valid. If it violates even one of them, then it's invalid. Now, it may seem kind of odd that you can do the test with just these 3 rules and they work, but interestingly enough, they do. And this can be demonstrated. So we can take example number 1. We have no dogs up for adoption. At the animal shelter are pedigree dogs. Premise 2, some pedigree dogs are expensive dogs. Conclusion, some pedigree dogs up for adoption at the animal shelter are expensive dogs. So, how do we tell if it's valid or not? Well, again, by rule 1, we've got negative premise, but no negative conclusion. So, by rule 1, invalid. But how can we be sure? Well, we can use our diagram test to test it. So, to do the test, we need to know, what's our S term, what's our P term, what's our M term. So we go to our conclusion, and we've got some pedigree dogs up for adoption are expensive. So some SRP. So we know that expensive is P, pedigree dogs for adoption are S. So we go to premise 2, some pedigree dogs are expensive. So that would be expensive is P, so some MRP. And then our first premise is no dogs up for adoption are pedigreed, so no SR. So then we do our diagram. So premise 1, no SRM, shade, 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 shade. Premise 2, some MRP. and our conclusion, sum SRP. And looking at that, we would need an X here, we don't got that, so invalid. Which is fortunate because the rules method showed it to be invalid as well. Second example for rule 2. Rule 2 is that at least one premise must distribute the middle term. So our middle term here would be keyboard players. So we've got all pianists are keyboard players, some keyboard players are percussionists, some pianists are not percussionists. And so it actually breaks two of the rules because it's got a negative conclusion, no negative premises. It also breaks rule 2 because if we look at M percussionist, not distributed here because in a sum claim nothing is, and in the all claim we've got all pianists are keyboard players, so keyboard players is not distributed, and so M is not distributed in anywhere. So it'd be invalid. I mean, it can't be doubly invalid, but it breaks two of the rules. Negative conclusion, no negative premises, and the middle term is not distributed in a premise. Lastly, example of breaking rule 3, which is whatever is distributed at the conclusion is going to be distributed in its premise. So looking at our argument, we have premise 1, no mercantilists are large landowners. Premise 2, all mercantilists are creditors. Conclusion, no creditors are large landowners. So in our conclusion, we have the subject term, well, the S and the P term, both distributed. So, since whatever distributes in the conclusion is going to be distributed in its premise, both of those have to be distributed in the premises to be valid. So we go to premise 1, and that's fine. We've got large landowner being distributed because in a no claim, everything is distributed. Then we go to premise 2, all mercantilistic creditors. It's not, because in an all claim, only the subject is distributed, so it fails that test. So it'd be invalid. So look at those two ways to test arguments. Way 1, do the diagram. Way 2, rules method. I technically have way 3. Way 3 is guessing, and since it's either valid or invalid, there's a 50% chance getting it right. Before pressing on, anything about the rules that needs any more stuff? Okay, so that brings us to the end of chapter 8. So what things should you know from chapter 8? Well, main things are this. We have 4 categorical claims, which are labeled as A, I, and O. And so you've got all SRP, no SRP, some SRP, some SR not P. And we've got Venn diagrams of the 4 types. And we can translate the English stuff into categorical claims. And we had some handy rules. One only gives us the predicate of an A claim, which I remember by OPA. The only gives us the subject of an A claim, TOSA. Whenever is all or no times or occasions. Whenever is all or no places or locations. Then we saw the square of opposition, and we saw the 3 versions. But again, for the practical standpoint, for the test assignments, etc., we use the author's square-ish of opposition. Where we've got the, those 3 relations. Namely, we've got the contrary, they both can't be true, subcontrary, they both can't be false, and contradictions where they're opposite. One is true, one's false. In terms of how they'll show up on exams, assignments, quizzes, etc., again, kind of the usual thing is definitions, what is, what are contraries, what are subcontraries, what are contradictions. Another common thing is to give, say like, if all cats are mammals is true, then some cats are mammals must be false, or similar sort of question using this square of opposition. We then looked at the three categorical operations: conversion, switching the subject and predicate; obversion, where you do the negation and then negate the predicate; and then contraposition, where you flip the subject and predicate and negate both. And we saw that some of them, namely aversion applies to all of them. The conversion applies just to the symmetrical claims, all, none and some are. And the contraposition applies to the non-symmetrical, namely the all S or P and some S or not P. Then we looked at how you test them with Venn diagrams, and then we're done with that. Before heading to our final chapter, chapter 9, anything about 8 that needs more stuff? Chapter 9 takes us into true functional logic, which is basically a form of modern logic. It was developed over the course of a few centuries and is kind of the next step up. You're all, in a way, sort of indirectly familiar with true functional logic because, quite literally, laptops, smartphones, PlayStations, Xboxes, switches, etc., both the game and literal electric switches, they all run true functional logic. So, really important stuff. So our objectives in Chapter 9 are these. 1, the basics of truth functional logic and the truth table. Secondly, going from normal English to pure symbols. Now, with the categorical logic we saw, even though it's technically like a different language, it looks just like English. In fact, you might say, well, it's pretty much kind of formalized English. Because if you have something in standard form in categorical logic, it can still have, in fact, will have normal words, like all cats are mammals. Now, when you get to truth functional logic, when it's been done, fully truth functionalized, you won't have any English left at all. I mean, we can put things truth functionally in English, but you end up just purely with symbols. So the only things you'll have in there will be the claim variables, the connectives, and parentheses. So this is sort of the most basic of logics that hasn't got any actual words, so to speak, in it anymore. We'll also learn to build these truth tables, and the end game, just like with categorical syllogisms, is getting from normal sloppy English, getting into symbolic form, building the argument for premises and the conclusion, and then seeing whether it's valid or invalid. So the end game with deductive arguments is always, is it valid or invalid? Now, truth functional logic will be rather more complicated because instead of there being just 4 possible sentences, all S or P, some S or P, no S or P, some S or not P, there's potentially an infinite number. So going from 4 to infinity, quite an upgrade. Also, unlike categorical logic, which just has the categorical syllogism, 2 premises, 1 conclusion, deductive arguments, truth functional ones, in theory, obviously not in practice, could have an infinite number of premises, but still, of course, 1 conclusion. So with truth functional logic, there's no just 1 argument type, there's no fixed number of premises, still a fixed number of conclusions, always 1, but you could have, again, potentially an infinite number of arguments. So a little more tricky. So what is this truth functional logic? Well, as the name sort of entails, implies, it's truth functional. So what does that mean? Well, truth functional logic is a logic based on truth functional claims, which of course runs us in a circle because what's truth functional? kind of informally put, truth functional means that the truth of the whole thing, the whole claim, depends on the truth of the parts, is a function of it. So the idea being is that it works in such a way that if you know the truth of the parts, you know how the connectives work, you would know the truth of the whole thing. And again, it's something you work with every day, perhaps without realizing it. If you're looking at your laptop or your phone, it's running truth functional logic. It's doing the truth functional thing. And as you can see, it's a pretty amazing, powerful logic because YouTube, that's truth functional logic, and it's able to do all this pretty cool stuff. So, what are its applications? Well, starting with the boring ones, set theory is truth functional logic. Also, it is the foundation of all mathematics, supposedly. Getting to more cooler things, electronic circuits are based on truth functional logic because they work with being on or off. So wiring diagrams, for example, which is not particularly exciting, but it's good to have light. And the simplest one, of course, would be a simple on-off switch. It's on or off. And of course, there are more complicated ones. Everyone's probably encountered, where you have like a hallway and there's light switches on either end, and somehow it knows, whenever you flip a switch, it knows like to go on or off. Now then, of course, you get to the more interesting electronic circuits. Again, the processor that makes up the brain of your laptop, your smartphone, PlayStation of various types, Xboxes of various types, etc. And so all of that stuff runs on truth functional logic. So why learn this stuff? Well, one reason is learning about the structure of language. Although truth functional logic is an artificial language, we made it up, as we kind of make up all languages, by studying it, we learn how to see the logical structure of language and use it, or misuse it. Also, it's kind of a good entry point into learning how to work with a precise, non-mathematical symbolic system. Kind of an entry into, that would eventually lead to like programming languages, etc. And of course, it enhances, if your goal is to get to truth, communication, being more exact, more precise, and figure out what people need. Now, the heart of this form of truth functional logic is the following stuff. Now, as I mentioned, like with categorical logic, truth functional logic is a language. And it's an artificial language built on our natural languages. But when we get to the pure form of truth functional, we've only got the following stuff. We'll have no words. It'll just be what are called claim variables, which is a fancy term for P, Q, R, etc. And they're variables like in math. They're like a stand-in, like a map is a stand-in for the real thing, or a token in a board game is a stand-in. So the claim variables could be anything. Typically, each one is taken as a single, particular aspect of the claim, particular claim, but you could stuff anything in there. Well, any type of claim. Now, traditionally, philosophers use P, Q, and R, just because. And you could use any other letters. And if you really wanted to, you could use anything that it consists of. So if you want to use like little cartoon animals or something, I guess a Pokemon or whatever, you could, as long as you were consistent. That is, these are just stand-ins for claims. Now we'll also have, as we'll see in the future, the connectives. We'll have the connective of not, and, or, and if then, and of course parentheses. So our language consists of these three things. A properly formed sentence in truth functional logic will just be claim variables, connectives, 0 to 4 or more, and parentheses, 0 or more in pairs. Now, truth functional logic of this type has two critical assumptions. One is that every claim is either true or false. Second critical assumption is, but not both. So it's binary in the sense that two options, true or false, and there's the excluded part where you can't have something being both true and false. Now there are logics that aren't binary like this. They have more than just two values. They have multiple values or ranges of values. Now we can get quite away with just two options. And as I mentioned, unless you have some sort of new and interesting computer, your computer runs on this true functional logic. It has the states of being on and off, although we represent these with zeros and ones. So next time when we meet on to more truth tables, so have a good rest of the week, and I'll see you on the Tuesday.